Hello, everyone. Welcome to Discrete Math. This is September 1st, Wednesday, 2020. Hello. If you want to participate and ask questions, you may do so in that way. Discord chat. I'm sorry, not Discord chat. Twitch chat. But remember that is public. Or you may do so in Discord chat, which is, of course, restricted to the people that are currently enrolled in the course, or one of the two courses. Okay, today we are going to be principally talking about the three counting principles. That should be a semicolon there, not a colon. That's annoying. It's and those things. And then we're also going to be talking about lists, strings, permutations, and binomials. And of course, we're going to talk about the quiz. Before I begin, I've got a couple of announcements. There were two kind of projects. One, figuring out how to do the retakes. So retakes are going to be done. We've kind of figured out how we're going to do it. We're going to do it on paper. So just like you can right now give show your work for partial credit, where you can scan it and then upload it. For the retakes, it's going to be, that's the only thing you do, is you just scan and upload the paper. So the paper quizzes are going to be the retakes are going to be the paper quizzes that I scan. They're not going to be multiple choice or anything like that. So that's how we're going to handle retakes, but I haven't set it up yet. And the other thing that people have been asking me for is a different textbook, because they want, you guys, apparently some of you want problems, and you to play with and things like that, and another thing to read. That's just not my rantings on the paper, and that seems like a reasonable request. And the current book for this material, now we're definitely going to be using this book. We're definitely going to be using this book when we get to number theory. But people have been complaining that I've been complaining that the current book really doesn't have good problems for this stuff because we're doing it first. They're assuming that you know a whole bunch of stuff before we get to where we are. So what I did over the weekend was I went on the library and found a textbook that is free, which is very important to me, that has some of this stuff. So I'm going to add it to the syllabus and to the Canvas later. But if you want to get more problems, maybe see a slightly different perspective on it, this is the book that I settled on. It's called Fundamentals of Discrete Math for Computer Science. If you search for it from the library, it is 100% free. They've got a first and second edition, all of them free to download through Springer, free for USF students because you are, through the library. So you go through the library, you get the link, you go into the link from the library, just like the other book, not Rosen, but the other one that I already chose, the other second textbook, and you can access this one for free as well. Are there any questions about that? So this is it's another textbook with problems in it. Okay. All right, so there don't seem to be any questions. By the way, I do have a TA. Very nice. The other thing, you mean we submit them as a comment? No, so you know how right now when you submit the paper quiz, but not the paper quiz, the multiple choice quiz, you have at the bottom there's a question that says if you want to show your work. Well, the quiz for the retakes is going to be upload your work. And it's not going to be, it'll be a quiz, just like right now where it says quiz 1A, there'll be a quiz 1A retakes. And what it'll do is it'll have a bunch of questions on it that say things like show your ID, show your workspace, but then it'll also have hold up your blank quiz, fill it out, hold up your completed pages, upload your pages to this question here. So you'll be doing the retakes just on paper. Okay. So that seems to be the questions. Anything else? All right, so let's talk about this quiz. And I'm going to do things slightly differently today because I'm going to be talking about the quiz and the lecture at the same time. And I'll show you what I mean in a sense. I chose the quiz questions to be leading, right? Okay. So for this first question, I asked you to enumerate the power set again. So this, as you recall, means power set. Which is the set of all subsets. Okay. So I asked you to enumerate the power set. By the way, I have a tendency to do things. You'll notice that this is a repeat question. I have a tendency to do these things when they're important and people miss them. I sometimes put them on there again and again and again and again and again. And if you ask people that were in the class last semester, they'll tell you, oh yeah, there was the problem for the binomial theorem was on all 4 tests. So I have a tendency to do that, especially when I think it's important. So this is the list. So how do we feel about this list of sets as 2 to the a, 1 to 5? Five poll seems a little slow. Excellent. Well, I do put, so someone's saying, why don't I instead put the ones you got right? Well, these are the ones that most of you got. Many of you got right these. I'm sorry. Many of you got these right. So, if you get them right the first time, 3 points. I do have a tendency to do this, especially if I think it's important. It's not so much the stuff you get wrong, it's the stuff that I think is really, really important. So there's kind of a trade-off, right? If everybody got a question wrong, you'd probably see it again, even if it wasn't important. But if, half the people got it right, half the people got it wrong, it's semi-important, you might see it again. If it's really, really important and everybody got it right, you'd still see it again. So, there's kind of a trade-off between those two things. Okay. Well, this is interesting, though. Note here that A choose 0 and A choose 1. So this set right here is A choose 0. I mean, the set containing this set here. And the set containing, this set here is A choose 1. I'm sorry, these 3 sets here are A choose 1. The set containing these 3 sets here are A choose 2, as you see below. This is A choose 2 is the set of the pairs. AB, AC, BC, all as a set. And then A choose 3 is right here. So on the one hand, I could count the power set, right? But on the other hand, I'd be counting the exact same thing if I counted this set, then these 3 sets, then these 3 sets, and then this set. In other words, I could count 2 to the a, but on the other hand, I could count the size of A choose 0, and A choose 1, and A choose 2, and A choose 3, and add them up all together. And they would both count the same thing. Which means that in general, because remember that, the definition of n choose 0 is, the size of the collection A choose 0, where A has size n. This means that 2 to the n, right, equals, n choose 0 plus n choose 1 plus n choose 2 plus blah, 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 n choose n. And that's a proof. On the one hand, I could count this set, the power set, this way. On the other hand, I could count all of the pieces of the power set and just, add them up all together. How do we feel about that? One to 5. How do we feel about that? There we go. This idea that if I'm doing 2 things the same, if I'm counting the same thing 2 different ways, the formulas I use better come out to be the same thing because I'm counting the same thing, right? I could break up the power set into those parts and then count each part and add it together, or I could just count the whole thing, and I've counted the exact same thing. Okay. All right. Any questions about number 1? A. B. All right. A choose 0. The set here is the set containing the empty set. Now, as I say on the little aside, if you said 1 because 1 equals the set containing the empty set, when we construct the natural numbers, you're a smartass and you should have picked the better answer. So I'm not going to give you credit for it. If you said 1 because n choose 0 equals 1 and you misunderstood the problem, obviously I want to measure the fact that you misunderstood the problem. How do we feel about that answer? That this thing that I'm asking for contains a set, right? There is a 0 element subset of A. It's the empty set. It's got nothing in it. There's one of them, right? But what I want to do is I want to state what that set is. So H of 0 equals the set containing an empty set. So the difference between, the question is, can I go over the difference between the empty set and the set containing the empty set? Yes. So let's say I have a directory. Let's see, we'll call this mkdir set outer. Let's go into set outer. And let's show you this so you can actually see it. Let's see, is there a way to make this bigger? Yes. There we go. Okay. Yeah, so set outer, mkdir empty set. So the empty set contains nothing. However, the set containing the empty set contains the empty set. I tried to hold control and do... Oh, it does work. Okay. I tried to hit control plus. That usually works too. That didn't work. Thank you. Yes. Yes. So it's like the empty box example. I've got a box that's empty, and then I've got a box that holds the empty box. Okay. Same kind of concept thing. I've got a directory that is empty, and then I've got a directory containing an empty directory. And it's got one thing in it, that directory. That empty set. Okay. All right. I knock that aside. All right, the size of A choose 2, well, that's 3 choose 3, that's 3. There are 3 of these sets right here. There are 3 pair sets. And the size of A, comma, empty set together, well, that's 2, right? It's that bag, that outer bag has 2 things in it, right? It's got a copy of A and a copy of the empty set. And this thing's not recursive. No. So there's a question in Discord. I'm going to read it. So with 1B, choose 2 is like choosing the second thing in a list. No, it's choosing all of the pairs of things from A. So let's say A was these 1, 2, 3 cards, right? The 10 of hearts, the 8 of clubs, and the 8 of hearts, right? So this is here. This is the no, not the cards. Okay, fine. No, you get the cards. So I've got these three items. Now, what are the pairs? Well, there's one pair, 8 of hearts, 8 of clubs. 2, 8 of clubs, 10 of hearts. And 3. So there are 3 separate pairs that can be made from these 3 cards. Okay. Are there any questions about that? There's a question. Do you need to be familiar with the codes I'm typing? No. The point of me doing it is to get you familiar with it. So I do it because now you've seen it. You're kind of, you're choosing an IT or cybersecurity career. You should see it. I could do it in Windows as well. The make dir command would be the same thing. I'd be using dir instead of ls. Okay. You're saying the binomial question was worded differently. I'll get to it in a minute. Okay. So 1E. This is a set with 2 items. Okay. It's got 2 items in it. The set A and the copy of the empty set. It's got a deck of cards. All in a nice little box. And then it has an empty box. Okay. Are there any questions about that? And why does it keep making that noise? It's annoying me. Okay. Yes, cardinality because I have the bars there. All right. Okay. All right, this binomial question. There are a couple ways to get at this, but the point is, and I'm not sure which one was. People have been saying that it was different on the quiz than it was on paper. It was worded differently. Oh. I'm looking at it. I'm sorry. I want to confirm this fact because it bothers me. So, and it's not that I don't believe you. I just want to see what I wrote. Oh yeah. Okay. So the way that it worked. Okay. So I didn't say don't simplify the binomial coefficients, but you didn't have a choice. So a plus b equals which of the following? It's 4 choose 0, a to the 4th b. This is the expansion using the binomial theorem. This thing does not. Okay. So this equals 1. This equals 4. 4 choose 2. Is 4, 3. I messed that up then, didn't I? There are 2 correct answers. Ouch. Okay. So I have to give everybody credit that picked this as well. I'm sorry. There weren't supposed to be 2 correct answers. There was only supposed to be 1 correct answer. It did say don't simplify, but it didn't say don't simplify in the on this quiz. It only said don't simplify on paper, which I would say is controlling, except I thought that I deleted that answer and apparently I did not. Because I didn't want there to be two possible answers there. Okay. So in that case, I will fix that. I will give everybody who got who answered this answer full credit. Fair enough. Okay. But I didn't want them simplified. I wanted us to talk about them unsimplified. So there's two pieces of this. First, why does it not matter that which one of these I do? Why are those two things the same? And well, first it has to do with because I can add and I could, addition and multiplication, the order doesn't matter, but within the two of them, right? It matters which one you do first, addition or multiplication. But it doesn't matter which two pairs of numbers you multiply first if you're multiplying a whole bunch of numbers, and same thing with adding them. Right? So the other thing is that there's something called binomial symmetry. So if, this is just preamble stuff. N choose k equals n choose n minus k. Okay? And the proof is as follows, right? On the one hand, I could count n choose k. That's the number of ways I could deal k cards from an n-sized deck, right? So 52 choose 5. The cat knocked over the card cam earlier and then went outside so you couldn't see the cat. So, right, so if I've got n choose 5, that's the number of ways I could choose 5 cards off this deck, right? But notice what happens when I choose 5 cards off this deck. I also create a pile of 52 minus 5 cards. Okay. Does that make sense? Let me do it again. If I have a deck, if I have 10 cards, now let me count the number of ways I could deal 4 cards. But every time I count a way to deal 4 cards, I've also counted a way to deal 6 cards. Every time I count one way to deal 4, I've also counted a way to deal 6, because there's 6 cards left in the pile. And that's the symmetry of the binomials. Okay? And that's what this says. Every time I count a deal of k cards, I also count a deck of n minus k cards. And as an immediate consequence of that, I want the free one. As an immediate consequence of that, Pascal's triangle is symmetric. Right? 1 choose 0 is the same as 1 choose 1. This is 2 choose 0. 3 choose 1 is the same thing as 3 choose 2. And 4 choose 1 is the same thing as 4 choose 3, and so on and so forth. And that entire proof, here's a proof. Remember proofs from geometry? No one pulled out a deck of cards in geometry class, right? In high school? No. This is not that complicated. All I'm saying, but they're subtle, they're weird, they're tricky. Right? But all I'm saying is if I count k cards, if I count a way to create a k card subset, I've also created an n minus k card subset. Okay? All right. And that's what that says. And that's a proof, a perfectly good proof, a perfectly good and able proof. We'll put a little square at the bottom, QED right there. What was to be shown? Right? That's it. How do we feel about that, 1 to 5? There's a question about taking a binomial to an nth power. I'm not quite sure what you mean by that, but we can talk about it. Let's talk about that later because I'm not quite sure what that question is. Okay. Is there a choice one makes when counting the number of ways a hand is dealt? In a sense, yes. So I'm gonna come back to that problem, that question. It's a good one, and I'll come back to that when we get a little bit more precise in what we mean by choice. Okay. Name one thing you found memorable last lecture. I hope it's the binomial theorem. This says k is in n plus 1, which is a very clever way of saying that k is in this set here, by the way. And this is all preamble. Don't worry about it. But this is a clever way to say k is in the set 0 ... n, including the endpoint. And that's all that says. Remember, because that's what n plus 1 is, that set. When you construct them. Yeah, but you don't add them together like I think you're saying. Let's talk about it later. I like that. I like that thinking. But let's talk about it. I'm not quite sure the property you're getting at, but we can talk about it. I'd be happy to. But it is the case that n choose k to a power is the same thing as n choose n minus k to a power. If you wanted to do something like that. Okay. All right. Let's go there then today. So today's overarching goal is to obtain and prove a formula for n choose k. Now, someone's going to pull out a factorial formula. I don't want to see it. We're actually going to figure out why that's the formula. And the why, and then the simplified form of the formula, once you understand the simplified form of the formula, it's easier to remember. Okay? That's what we want. We want the simplified form of it, which is easier to remember, but you have to understand what this new notation means. Okay? So, in general, we're going to have 3 major counting principles. Okay? So today we're counting about the 3 counting principles. We're going to talk about the cross product briefly. Then we're going to talk about lists, which have 1,000 different names. And then we're going to talk about the factorial and the falling factorial and the formula for n choose k. Okay, that's the goal. Whether we get there or not is another thing. Now, that factorial formula that people are throwing up in chat, thank you. You have it slightly backwards, but okay. It's you need a k factorial there instead of an n factorial on the bottom, because otherwise they cancel. It'd be like n factorial over k factorial times n minus k factorial. But we'll get why that's true, and that's actually not the easiest way to remember the formula. There's a much better way to remember the formula, so we're gonna get to that. It gives you the same number, but it's very simple to remember. Okay, so there are these 3 counting principles. this is generally what we say. If I want to say, or I could add, and we did this last time. Do you remember this one? I wanted to count 5, choose 2. So this was using the principle of or. I could start with the king of diamonds. And then I would have 4 choices about which one to put in the pair with him. Or I could start with the 9 of diamonds, and I'd have 3 choices left. Or I could start with the 8 of spades, and I'd have 2 choices left. Or I could start with the 4 of clubs and have 1 choice left. Okay? So let's do that again, right? The principle of or. And this is actually an example of both. Or and. Okay, so last time we did the principle of or, right? So I started with count 5, choose 2. So if I have 5 cards, we'll just call them ace through 5. Of the same suit, I don't care what it is, diamonds. Right? Now, I count, there are if I pick the ace, there are 4 cards to match it with. Or I could pick the and this is called the principle of or. All of these sets, all of these things, I'm not overcounting, right? That's the point of saying or. Let me move this out of the way. All of these things are disjoint. In other words, once I've counted a card as the original card, I've discarded it. So I'm not counting repeats. How do we feel about that 1 to 5? What I'm doing here. I'm picking the first card and then matching it. Then I discard it because I don't want to count using that card again. Then I count the next card and I discard it after I've counted the 3 that can match with it because I don't want to count that card again. Then I've discarded, I count the 3rd card with the 2 that are remainder. Or then, I've got 1 card left with 1 remainder. So what I get is the ace has 4 cards, 4 possibilities. The 2 has 3 possibilities. The 3 has 2 possibilities. And the 4 has 1 possibility. And if you want, the 5 has no possibilities. And that gives me the answer for 5, choose 2. I've counted the number of ways to do it. Well, 4 or 3 or 2 or 1 or 0, which gives me what number? Anybody? Hey, there we go. Okay, and that's one way to figure out what 5 choose 2 is. Incidentally, this is also called a triangle number. Because it looks like this. So it's also called a triangle number, so you can sometimes see that. And Adobe is crashing on me. Maybe that's why it keeps making that sound. The Adobe installer. Okay. So that's the principle of OR. How do we feel about that? 1 to 5. The principle of OR. If I would say or then, add. General rule, right? It's the principle of counting disjoint sets, the unions of disjoint sets, but we're going to call it the principle of OR. The principle of AND is a little different. The principle of AND says if I would say and then, multiply. So let's look at Pascal's identity. Okay, it's a very good example of this. Let me make sure I've got the exact same one that you want. Yes. Okay. Wikipedia calls it Pascal's rule. And it works like this. No, let's not do that one. That one stinks. Sorry. Let's do one of the other ones. I think what he's calling Pascal's rule, what's called Wikipedia's Pascal's rule, I think is actually called Pascal's identity on other sites. That's not the one we want. That one's got an OR in it too. Oh, let's see. Ooh, this one's a good one. No, not that one. Let's see. Binomial identities. Does anyone have any questions, by the way, while I'm fishing around for something that I should have had off the tip of my tongue earlier? No, Dixon's identity stinks. Takes too long. All right, let's do this then. Let's count the number of straight flushes in a deck of cards. Or let's count the number of flushes in a deck of cards. Okay. Let's not do one of the identities. Let's do count the possible flushes. That's fun. So if you're not familiar with a... yeah, I know there's a typo in my profile. I haven't fixed it yet. Thank you for sharing. Somebody told me yesterday. So does everyone know what a flush is in poker? So a flush is getting 5 cards of the same suit. Okay? So, for instance, if I have all of these clubs, and I'm going to count the straight flushes and royal flushes as flushes for the moment. Okay, so how many ways are there to get 5 cards of the same suit? Okay. This is actually more than a flush because the straight flushes and royal flushes don't count as simple flushes in poker. They count more, but we're just going to count them all together. How many ways are there to get 5 cards of the same suit? Well, how many cards are there of the same suit? How many cards are clubs? How many cards are clubs? Now, there are 13 clubs. Okay? So, how many ways are there to draw 5 cards from the 13? How many ways are there, without order, of dealing 5 cards from 13? How many possible subsets do I have? How many possible subsets of 5 cards do I have from a 13 card set? The answer there are 13 choose 5 ways to be dealt 5 cards from a particular suit. Now, how many suits are there in the deck? If I choose clubs, there are 13 choose 5 ways for me to get the 5 clubs. But I've already chosen the 5. I've already chosen the clubs. Now, how many ways are there for me? How many suits are there in the deck? I know that the spades are the swords of the soldier. I know that the clubs are weapons of war. I know that diamonds mean money for this art. That's not the shape of my heart. Song too old for you? Yeah, they're 4. So, in order to get flush, flushes. Four, I choose the suit. There are 4 of them. And then so first I choose the suit. And then I choose which 5 cards I got from that suit. So first I count the suits, and then I count the cards from that suit. Well, why is it not 4 factorial? Because there's only 4 suits. There's 4 choose 1 suits. Right? There's only 4. There's not 4 factorial of them. And then one person put 52 choose 5 minus 13 choose 5. Now, that would count all of the ways to get a hand without one of the suits. So if I wanted to count the number of ways for me to get dealt a hand with no clubs, that's what that would count. 52 choose 5 minus 13 choose 5 would choose that. How many ways are there to get no clubs? But that's not what we're counting here. How do we feel about that 1 to 5? I mean, I can also do this with the rule of OR. Right, there are 13 choose 5 ways to be clubs, or 13 choose 5 ways for diamonds. I don't feel like writing all that out. Or 13 choose 5 ways for hearts, or 13 choose 5 ways for spades. I think my spade looks like a club. Right, and I could add them together, but that would give me 4 times 13 choose 5. Okay. Well, another application in this is called list. So this is a direct application of the rule of AND. Okay, so a little note here. Depending on what you're reading, a list can be called a string, or a word, or a finite sequence, or an array, or a k-tuple. Okay, so let's talk about real fast what this k-tuple business is. Let's talk about the cross product of a set. Let A and B be finite for the moment sets. Okay? For the moment, we're just going to deal with finite stuff. It's the same definition if you do infinite. But whether or not something exists, there's an axiom called the axiom of choice that we don't want to get into. So we're just going to say finite because we know that these exist. Okay? With our current set of axioms without having to go further. Then A cross B is the set of ordered pairs A, B, so that A is in A and B is in B. Okay, so example. I didn't want that red. What does A cross B equal? Okay, right? And how many elements are there? Well, and then I choose the element from A, and then I pick the element from B. A times B. Any questions about that? 1 to 5, how do we feel about that? Okay. So that's all it is. Now, what we call a word. So I'm going to give this is the definition. I'm going to use the string definition first, but they're all the exact same definition. They're a list, a string. All of these things are basically the same thing. I'm going to use this as a I'm just going to use the word definition because we're going to use it again later in the course when we talk about strings and we talk about when we talk about a bunch of other things. We're going to use word when we talk about machines. So I'm just going to start that way. So okay, let A be a set. Okay. The K word is an element of A cross A cross A cross dot 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 cross A. Okay. How do we feel about that definition? In other words, and that's all that means. It's a clever way of saying something kind of obvious, but it's math. We want to be formal, okay? So these things are also called 3 tuples from A. Okay. If if A if it would be unambiguous, we would write AAA or ABA or etc. So it's just what you would think. A word of length 3 made from that alphabet. Right? ABA 010 if I'm using binary. Okay, so let's see. Are there any questions about that? 1 to 5, how do we feel about that? I'm looking in here and people are talking about other things. Um, did I send out the wrong notes rubric? Is that what's going on here? If so, I will fix it. I may have sent the one from calculus instead of sending the one from discrete, but I thought I sent the one from discrete. All right. So the question is, how many words are there? So if the size of my alphabet equals 5, If I've got 5 letters in my word, I got 5 blanks, and I've got, I've got 4 blanks, and I've got 5 possible letters to go in that blank. How many possible words are there? There's a question. What if it's A as a list and AB as a list? Those are 2 different words. One of those is a 3-word and one of those is a 2-word. So how many possible words? Let's say A equals A, B, C, D, and E. Okay? Now, how many possible 4 strings or 4 words can I make from that? Well, let's see. I could do A. That's a word. A, that's a word. And et cetera, et cetera. I'm sorry, there's too many of those. B. I'm sorry, this should be a B-A. B. I'm not even through the B's yet. And actually, I should do C. D. There's a lot of them, right? And notice that things can repeat. So how do I get at this? Yeah, there's 5 to the 4, right? There's 5 times 5 times 5 times 5. In general, if size of A equals n, there are k to the n ways, there are k to the n possible words of length k. No, they're n to the k. I'm sorry. They're n to the k. I got that backwards. There are n to the k ways possible words of length k. That was right. That was wrong. Okay. Right? Because I've got k blanks and I've got n possibilities for those blanks. Now, a real world example. What if A equals 0, 1? How many different messages can I give with 6 blanks? And this is a problem you've seen before. Yeah, 2 to the 6th. So you've already actually seen this before. This is just a little bit more general. Now my bits can have different size. And don't let this confuse you. This n and this n are different things. So the 2 to the n in this formula is actually the k in that formula. That's just to confuse you. That's just because mathematicians don't like you. Okay? All right. And I don't mean you in general. I mean you in particular, Sir Critical Curiosity. Just so you know. Okay. So how do we feel about this 1 to 5? That joke works better, by the way, in a physical classroom, right? It's funnier when you can pick on the person that's looking at you strangely like they don't like it. Then it's funny. All right, let's see. All right. Now, what happens if I don't allow replay? What happens if I don't allow repetitions? This is called a permutation. Okay. So let's let the size of A equal n, and the blanks equal k. And this is why I chose up here the n and the k in the way that confused you when I went to binary again. Because I had an n for my k when I talked about binary, because I was always using a base 2. And there's a reason why I inflicted that torture on you, and the reason why is right now. I guess at the very beginning of class, I should have said 2 to the k instead of 2 to the n. But I can't go back. All right. So I've got k blanks and n possible letters. Oh, and n is greater than or equal to k, obviously. Or there's no point. Now this is what's called a permutation. So I can't use repeats. So some of you have seen the permutation number before. We're going to get rid of that notation. We don't want it anymore. This is our notation for the permutation number. The number of possible permutations is called n falls k. Okay. All right. So we've got a new word, n falls k. Well, what is n falls k? Let me show you why we call it that. So let's say, example. Let's say that A, now let's do A equals. A equals A, B, C. And K equals 2. All right, so how many ways are there to do this? How many ways are there to pick the first letter? Three. How many ways to pick the second? So 3 false 2 equals 3 times 2. All right, let's do another example. Let's do the size of A equals 15 and K equals 5. How many ways to pick the first letter? Well, there are 15 ways to pick the first letter, 14 ways to pick the second letter, 13 ways to pick the third, 12, and 11. All right. Now, let's suppose that A equals 4 and K equals 4. Well, there's 4 ways for this one, and then 3 ways to pick the next one, and then 2 ways to pick the next one, and then 1 way to pick the last one. We give that a special name. We call that the factorial. Okay. How do we feel about that, 1 to 5? The computation of a permutation number. Did I lose my, there we go. So in choose K, in false K, I'm sorry, is called, also known as the falling factorial. It is the number of ways, it is the number of K words from an n-size alphabet with no repetition. And the formula for it, in false K equals n times n minus 1 times n minus 2 times dot 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 n minus K minus 1. Right, because here was, if you look up at here, if you're confused about that formula, think about 15, choose 5, okay? It's 15 times 14 times 13 times 12 times 11, right? And this right here, that last term, right, I fell 5, so that was 15 minus 5. Oops, this should be a plus 1. I'm sorry. 15 minus 5 plus 1. Okay. How do we feel about that 1 to 5? Okay. All right. So we kind of get that. Now, let's go back. So we've got these two type things, right? We've got the number of ways right? In false k is also the number of ways to draw k elements from an n element set where order matters, right? That's the same idea. So if I've got my deck of cards, and when I count these things, right, there are 52 ways to choose the first card. If I'm picking 3, and order matters. Order matters. There are 52 ways to choose the first card, 51 ways to choose the second card, and 50 ways to choose the third card. So that's 50 falls 3. Okay? And notice here that order mattered. All right? So it's not like 5-card straight poker where the order of the card, the deal matters, right? If you're playing Texas Hold'em, the order of the cards actually matters. Not whether you get a flush or a straight, but the probabilities change because you bet after a certain number of cards are played. Same thing in blackjack. The order matters because the information you're revealed is determined by the order, right? So if the dealer has a 7 on top and is holding a king, that's a different hand than a king on top and then a 7. Their strategy is different. So the order matters, not in the final outcome in that sense, but in the way you would play the game. Okay? So you want those counts to be, you want the order to be counted separately sometimes. Other times you want to count the order sometimes, or the way the cards come out in order, the order in which the cards come out. But some other times you don't. You don't care, right? So if the dealer gives you 5 cards straight, who cares what the order is? Because they're all hidden. Okay. So yeah, 52 falls 3. Now, let's go back to our original question. Our original question was, can we obtain a formula and proof of formula for n choose k? Well, let's look at this. Let me ask you something. Let's say I wanted to count the ways to deal 5 cards off a 52 card deck and count their orders. Okay? So we'll call this the 5-card ordered hands off a 52-card deck. Okay, so the order matters here, right? 52, what's going to be my formula for finding this? It's my permutation, right? It's my falling, right? There are 52 falls 5 ways of dealing 5 cards from this deck in order, where the order matters. How do we feel about that 1 to 5? I got the first card, the second card, the third card, the fourth card, and the fifth card. And order matters. 52 times 51, and then 50, and then 49, and then 48. Right? So I want to count this hand in order. Now, on the one hand, I could just count that. On the other hand, and remember, I want to count the number of 5-card orders from this 52-card deck. Well, I could count the number of 5-card unordered hands, and then count the ways to sort those 5 cards. In other words, I could take 5 cards without order and then count the ways to order these 5 cards. Well, how many ways are there to order these 5 cards? How many ways are there to order these 5 cards? Well, there's 5 ways to choose the first one, 4 ways to choose the second one, 3 ways to choose the third one, 2 ways to choose the fourth one, and 1 way to choose the last one. There's 5 factorial ways to do that, right? So, on the one hand, I could just count the number of orders, 5-card orders. But on the other hand, I could count the number of ways and then the number of ways to order those 5. How do we feel about that 1 to 5? I'm counting the exact same thing. I'm counting the number of ways there are to get 5 ordered cards. Okay? The number of ways to get 5 ordered cards. I could just count the number of ways to get 5 ordered cards. On the other hand, I could count the ways to pick the cards, unordered, and then the number of ways to order them. In other words, in false k equals in choose k times k factorial. Do a little bit of algebra. And I get that in choose k equals in false k over k factorial. So the question is, how do I compute 52 choose 5? I don't. I compute 52 false 5 and then divide by 5 factorial. Which is the same thing as saying 52, 51, 50, 49, 48 over 5 times 4 times 3 times 2 times 1. Now, what was that formula you had before? That formula you had before with all the factorials, right? If I use that here, I would get, it would be 52 factorial over 5 factorial times 52 minus 5 factorial. Well, this here equals 52 times 51 times 49 times 48. I'm sorry, there's a 50 in there. Times 47 factorial, I just keep going, over 5 factorial times 52 minus 5 is 1. And that's where that formula comes from. Well, this was this formula, right? This is this silly little formula. I'm going to write this here, silly little formula. This is the one you find in your old textbook, okay? The one in your old textbook is n factorial over k factorial times n minus k factorial. But that's stupid. Who cares? Right? Because when you cancel these out, all you need is the false 5 or false k. And this tells you where it comes from. It's a better formula. If you memorize this, you've just memorized a number, you'll mess it up. If you memorize this, you've actually memorized why it is that way. It is that way because there are two different ways of doing the exact same thing. 1 to 5, how do you feel about that? Oh, well, I don't care about the silly little formula. I don't want you to know it. I don't care. The silly little formula is stupid. Right? This is the better formula. This tells you where it came from. Death to that formula. Death to it. It's stupid. goes away. This is the formula we want. Of course, now it just says better best, and we have no idea what it means. All right. All right. Are there any questions? Okay. So I went a little over. I'm sorry about that. I spent too much time looking for fun stuff like the formula to prove or the flushes and stuff like that. But today we went over the 3 counting principles, the or I could, the and then the on the other hand. So if I would say or I could, in general, I add. If I say and then, in general, I would multiply. If I say on the other hand, that's the principle of double counting. I'm doing 2 things the same way and they're probably equal. Not probably equal, they are equal. I'm doing 2 things the same way. I'm counting 2 things that are the same. Therefore, my 2 formulas for counting them must be equal. And then we use that to prove a variety of things. If you want a few exercises, there are exercises in that 6.3 of this book here. There it is. Of the Jenkins book. I will put that on WebAssign when we're done here. Next time, we're going to start getting into the logic stuff. I'm sorry. We need to do set operations first. So next time, we're going to get into unions, intersections, and set minuses. We have to kind of fill that stuff in. I'll put that right here next time, set operations. And then we'll get into some of the logic. Any other questions? You have had assignments. So there should be 2 problem sets. You've got 1 problem set that you've turned in already, and then another problem set due Friday, and then you've got quizzes. Those are the assignments. People wanted more problems, so I said that I would go find a book with more problems. I could put some suggested problems if you want on the notes before I PDF them and put them up. If you want from that book. But the assignments are the problem sets and the notes. They're not in the quizzes. So essentially the quizzes are homework because I'm giving them to you in advance, right? Yeah, stuff due Sunday, not Friday. I'm sorry. Yeah, Sunday, not Friday. My brain's on Friday for some reason. Any other questions? Okay, well, that's it. Sorry for going about 15 minutes over, but I did. But you'll get over it, right? I'm just kidding. I'll talk to y'all later, and thanks for our new TA.